Record. Okay. Assuming that works. All right. Hey, John. Okay, cool. It is 6:02. Let's get started. So my name is Brandon Vessel. I am the treasurer for ACE, and today I'm going to be going over RSA, SSL, and public-private key cryptography. So just a disclaimer, most of what's in here is completely harmless, but you can technically use this to make bad things. If you make bad things and you get caught, we will make fun of you. Do not make bad things. Do everything you do legally. So I'm going to go over what symmetric cryptography, well, I'm going to explain why symmetric cryptography is different from asymmetric cryptography. I'm going to explain what RSA is, how it's used. I'm going to do a short demo on how we can use it to do SSH keys and how we can use it to kind of encrypt our data, sign our data, verify our data. And then I'm going to go over how we can apply that to HTTP and just kind of the internet in general. So we've gone over some sorts of symmetric encryption before. John went over AES a couple weeks ago. It's basically you have a password to encrypt your data. You have some plain text, you encrypt it with a key, it's encrypted. Then you decrypt it with the exact same key. Public-private key is a little bit different. It's kind of like you have a safe and you have a key that can lock it, but it can only lock it. And you have another key that can unlock it, but it can't lock it. So if I encrypt my data with my lock key, I can't get it back unless I have my unlock key. And so the way that this works in this diagram, this is exactly the same scheme that RSA uses. This is where you encrypt some data with a public key. It's gobbledygook, completely unreadable. And the only way to get the original data back is with the private key. So in other words, if Bob wants to send a message to Alice, then Bob will encrypt the data with Alice's public key. It's public, meaning everybody knows what it is. And so the only person who can then read that encrypted data is Alice. If I intercept that random 6EB6, whatever that is, in the middle of its transport, I'm not going to be able to understand what it is. I can't understand what it is unless I have Alice's private key, which is private. And the reason why this is so cool, and the reason I won't get into the math too heavily, but the reason why this is shenanigans and it doesn't work both ways is because of a funky little math thing called modulus. Everybody here's heard of the remainder, right? 5 remainder 3 is 2. 3 remainder 5 is 3 because you divide 3 by 5 0 times and you have 3 left over, right? So this is great. This is a normal math thing. It's just part of division whenever you don't have, nice numbers. However, what happens when we try to go back the other way? It's not quite as easy. So, this gigantic number, the second to last one, right? Something 1 mod 10, right? You can divide 10 into that, but you have 1 left over. But what happens when we try to go back the other way? Well, it could be literally any number, 10x plus 1, where x is an integer. It's just, it could be anything. We have no idea what it is. I won't go and explain what this is, but if any of you are interested, this is what this looks like. This is what RSA uses for its key generation, encryption, and decryption processes. So there's some funky stuff with some prime numbers. You have to multiply some things. There's some intermediate values. So for example, n, it's the product of 2 prime numbers, which it's really hard when those 2 prime numbers are really big to actually get the prime numbers out of n, because that means you have to factor a really gigantic number. And that takes a lot of time, which is what we want if we don't want people to figure out how our key works. So math is hard. This isn't a math club. This is a cyber club. So we're going to skip this. We're going to go straight into how this is used. So Diffie-Hellman key exchange. What is that? I want to send a message to somebody, and we both have a private key and a public key. But how do we transfer data, right? I don't know their public key. They don't know my public key. Well, I'm sorry. They know my public key. I know theirs. We need a password so that we can send a lot of data really fast, right? Because encrypting with public and private keys is fun, but it's not as fast as symmetric encryption. So what we can do is we can combine our keys together and use that to make a special kind of one-time use shared key. Bunch of funky math. If any of y'all are interested, you can look this up. But what's happening is we're combining these numbers in our keys together to get a common key that's the same for both people. So that's this value here at the bottom, this 9. These are all small numbers. In real life, these would be gigantic. But they end up getting the same number. They'll represent that number as some bytes, and they'll use that as their encryption key to talk to each other. So that's how we can use public and private keys, when everybody has some, to actually talk to each other without having to, come up with some pre-shared key beforehand. This is essentially a way of deriving a pre-shared key. So how can we use this? Well, we can use this for SSH keys. So I go to here real quick. I didn't give y'all these, but the commands aren't really that hard. So I'm not in Linux, I'm in Windows. So I'm going to use SSH Keygen TAC-T RSA. So this is going to use the OpenSSL library, which is a library for doing cryptography things with public-private keys and elliptic curve cryptography. And this is going to generate a key in my home folder on Linux that I can then use to authenticate for other things. And so I chose, pick an RSA key. It picks an RSA key by default, but I want to make sure it's an RSA key. So I'm going to add that argument on there. Tells me one already exists. It's okay. I'm not overwriting my key. I backed it up. So we are going to overwrite the key that is currently there. And you can actually put a passphrase in, which you should do to encrypt your key. I'm not going to, because y'all don't know what my key is. So it's okay. But in real life, encrypt your keys, because if someone gets access to your computer, your file's encrypted. So even if they log in as you and they have access to all your files, they can't just rip your private key and log into a bunch of other things. So I have a public key. I have a private key. I can share my public key. So here's what I'm going to do. I'm going to copy my public key using this command to a server I have set up in the cloud. So brand is my username. This is the address of the server. This is the port SSH is running on. This is the command to copy key. So it's going to copy my public key to the server, and I have to log in like I normally would if I didn't have this set up. So I'm going to log in with my password. Presto. The key was sent to the server. It gets thrown in a special folder, .ssh, on that server. And so now what I can do is log in. I didn't have to put in a password. It just works. I just log in, no password, no nothing. So what this means is if you want to run scripts or something in the background, you can have all these file transfer tasks. Maybe you SSH and run a command and then come back. You can have all these just running, and you don't have to type in a password every single time you want to do it. And you don't have to have a password stored in your script for logging in, because, well, now your password's in plain text and it can get compromised. So that is how you can use SSH with public and private keys. So here's me running it. This is essentially what it looks like. So it stores your information in the .ssh folder in your home directory. Technically, if you want to have more than one key, you won't just save them as this ID RSA file. You're going to want to save them as a different file if you want more than one key. And then you can specify that in your actual SSH command. I'd recommend man SSH to read the manual. There's a bunch of arguments for that. But you can actually specify which key you want to use to authenticate. So if you have more than one server, maybe you don't want to use the same private key for every single login. You can have this public key over here, this public key over here, and log in with 2 different keys to 2 different servers. So if one key gets compromised through an attack method, you can still log into the other server. It doesn't compromise everything you have. Okay, let me go do my other demo. So this is the one I think I sent it in the ACE Discord in the announcement channel. There's a zip file. The only Python dependency required for that is PyCryptoDome. So that's what you would type if you were on Linux, just whatever Python version you have. It should install that. I have it installed already. So let's encrypt some stuff. That's fun. So let me go show you how this code works. How do I hide this? Can I move this? I can. Put that down there on the bottom. So I made a little library because the actual PyCryptoDome library is fun, but it takes a hot minute to actually understand what's going on here. So let me just walk you through some of these functions. So base 64 is a way of representing bytes as letters and numbers. It looks a little bit easier than just a bunch of ones and zeros. So I've encrypted this here to make the strings a little more legible. There's a function here for generating new keys. So this will call the library. It'll generate a new key. You specify which key size you want. I have 4096 here as a default because as a society, we're moving to where this is how big you want your key to be, because the smaller your key is, the easier it is for people to guess your key. As John's mentioned in some talks prior, really weak short passwords are really easy to brute force guess the solution. You just keep guessing things until you eventually get it. With public-private key cryptography, we have something very similar. You would essentially keep guessing prime number combinations or try to brute force factor the solution. There are many different ways to brute force crack someone's key. The easiest way to prevent this is to use a big key. So when we generate a key, we're going to use a number like this. You can go even bigger. You can go 8192. What is it? 8192. You can do that. The only problem is it'll take forever for it to actually make a key. So you trade some initial time setup for a really strong key. The keys used for, I think it was like Google, Amazon, those websites, they have their own key for authentication. For the longest time, those keys were 1024. They shifted to 2048. Only recently are we actually shifting to 4096 because quantum is coming up and computers nowadays are just really powerful. So use big keys. Big keys are better. Got a function for saving keys, loading keys from the disk, encrypting, etc., etc. So the first thing you got to do is make some keys. Make keys. .py. Done. Got some keys. So I've got some keys saved in these privkey.pm, pubkey.pm files. This is actually a standard for storing RSA private keys and RSA public keys. You have this header at the beginning of the file. You have a header at the bottom of the file. And then here in the middle, this is actually those numbers, those mathematics numbers. These. It's actually these numbers just encoded, because otherwise it would just be like raw binary, right? You can't read binary, but you can read text. So it encodes the integer value of these numbers as text. So what kind of text? This is base 64. They just had a part of that and they're able to recover everything from it. You only need part of it. Yeah. You get part of one of the numbers. No, you get one of the numbers, and if you have part of one of the other numbers, you can break it. Yeah. Because it follows the standard, these numbers have to satisfy these equations, all of the equations. You can guess what the numbers are going to be based on what information you actually have. So we can make some keys. We can encrypt some data. Did I type my command right? Yeah. So I can encrypt anything I want. I can encrypt hello world. It will read my private key into memory, or no, I'm sorry. It reads my public key. You can't encrypt with a private key. As fun as it would be to encrypt something with a private key and send it out and unencrypt it with the public key, the math does not let you do that. You have to encrypt with the public key, and then you can decrypt with the private key. There's another thing you can do, I'll cover in a second, for private to public, but this is what you do with the public key because everyone has it and they want to send you things. So we take a message, turn it into a string. We pass it to this function, which is going to encrypt our message with our public key and return some random gobbledygook that's going to get base64 encoded and thrown into the terminal. Does anybody know what this says other than the fact that I typed it up here? It's no. No. If your professor just gave you this and said, hey, I'll let you pass the class if you can figure out what this says, you're not going to figure out what it says. It's impossible. You would spend until the end of the universe before you actually figured out what this said. But if you have the private key, you can decrypt it. So we can load our private key, get our gobbledygook text, our encrypted ciphertext, and we can actually decrypt it back into plain text. And we can print it. And so this could be, you generate a private public key pair, you give your public key to your friend, and you say, okay, cool. Well, from now on, if I ever send you gobbledygook, just unencrypt it with this. Boom, no one can read your communication. However, if your friend's private key gets compromised and you send them stuff, someone can still read what's going on in the middle. So you don't want to let your private keys get compromised. You want those to stay private. So there's another cool thing we can do. If we want to send people data using our private key, we can actually send them the plain text version of the data and use our private key to sign it. So what that means is we're going to take the data, we're going to take our private key, we're going to mash them together, and we're going to get a hash output, right? Everybody remember how hashes work, right? You chuck data in, you always get the same data out. This functions in the same way. You're taking certain aspects of the private key, plugging them into some math, putting it into a hash function with the message. It farts out this thing called the signature, which contains some other stuff that you then send with your message. It's in plain text, but what happens is when your message gets to its destination, you take the message, you take the public key, you take the signature, and you can actually verify that the message wasn't changed in transport. So here in this script, I'm generating two keys. I'm generating my public key and my private key. And then I'm generating, some other different keys, some evil keys. I'm gonna attempt to send a message and pretend like I'm whoever, right? Someone's trying to send a message. I'm gonna try and, oh, maybe if I just send my public key, then they'll think, oh, they'll just do the signature wrong, and it'll freak out and they'll accept the message. So it doesn't actually work. So I take my message, RSA is super cool. I encrypt it with my public key. It looks like this. I encrypt it with the private, I encrypt it with the public key for whoever I'm trying to send it to. It looks like this. You can decrypt it. This is the signature that you get if I sign that message with my private key, right? So you can verify the signature. So let's see, give me my function. Yeah, hash functions, lots of hash functions. There's a full standard for how this is done. It's It's a lot of math, but it allows us to verify messages using the message, the signature, and the thing. And so when I try to actually verify my message with my evil private key, I signed it with my evil private key, and then the recipient tried to use the signature I made with my incorrect private key with the public key of the person they think they're talking to, and it doesn't work. It says, no, this is in fact not the correct signature for if the correct person were to sign this message. There are a couple problems with this. Namely, if I send the same message, it's going to look the same way. Because this is a hash function, if I'm putting in the same input every single time with the same private key every single time, I get the same output. And so the signature ends up looking the same if I'm sending the same message. And so it's not implemented in this library, but you can force it with some arguments to some functions if you wanted to make an actually secure application. You would essentially pad some extra data on the end. So I'm sending the same message. RSA is super cool. RSA is super cool. However, it's adding some random stuff to the end, along with a little thing that says, by the way, the actual data you want is this many bytes long. So it's 1, 2, 3, 4, whatever, many bytes long. The recipient takes the thing, says, okay, cool. Signature works. How long is the thing I'm looking for? Okay, it's 12 bytes. Okay, I'm going to take those 12 bytes out. That's the thing I'm actually looking for. I can send the same thing every single time, but it's going to look different. And so you do run into some issues where if someone captures my packet and they resend it, they can do what's called a replay attack, where the recipient receives the same thing from me, thinks it's completely valid, and does whatever they're supposed to do with it. But you can also just encrypt it with their public key, and then no one can change your data. So not only is it verified that it's me, but the only person who can actually get the data is the recipient. There's just some fun things you can do with signing and encrypting. So that's fun. However, what can we actually do with that in the real world besides just logging into our servers? So in real life, if you're not a server administrator and you're just a normal person using the internet, you know that little lock you have in the top left corner of your browser when you go to an HTTPS website? Well, the S stands for secure, and what's actually backing that are two technologies, depending on how old your software is, SSL and TLS. They are essentially the exact same thing. TLS is the newer version of SSL. In layman's terms, the way this works is you have some super awesome, everybody trusts them certificate authority, which is that person with the CA hat. They're a person that's been designated by literally everyone, where I'm going to give them my public key. And anytime someone wants to talk to me, they say, hey, what's Brandon's public key? They get my public key. They can now send me stuff. I want to talk to them. Okay, well, what's Billy Bob's public key? Okay, cool. Now I can talk to Billy Bob. And so they're essentially a trusted, a certificate authority. They have the authority to send certificates, pieces of information that contain these keys to people for the purposes of contacting. So here we have a little diagram where the client and the server want to talk. The client requests a key for the server from the certificate authority. They then send some data to the server. The server will send back some more data that's signed with the private key, so you know who you're talking to. The client sends some more data. They establish a way of encryption. They don't use the Diffie-Hellman key exchange. They do something similar. They send a challenge. They send some more data. Because the client knows who they're talking to, the client trusts whatever the server says. So when the server says, all right, cool, we're going to use this encryption scheme. We're going to do this, 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 that, and that. Here's the key. The client can just communicate with the server. So there is an inherent layer of trust. We get our trust from the certificate authority. So here's a definition for the certificate authority I found on SSL.com. Pretty much what I was just saying. It's either it can be a company, it can be an organization. You can actually run your own certificate authority service on a server. Some companies will actually do that for signing pretty much any digital certificate, whether that's for SSL, TLS, or just some in-house communication scheme for a Git repo for writing code together. You can use these for pretty much anything. The key thing is you have to actually trust your certificate authority, because if they get compromised and the public key for google.com or amazon.com or whoever suddenly changes to something malicious, and then all the traffic gets redirected to a different server, well, now you trust the public key, but it's not actually the person who you think you're talking to. So very important they don't get compromised. SSL, this is what a lot of people think we're actually using, but we're not. This is the old standard that was replaced by TLS. It is a back and forth exchange by which the client and the server actually agree on how they're going to communicate and establish a means of communicating securely. I don't have a diagram for SSL, but I do have a diagram. Oh, I do. Never mind. I lied to you. I'm sorry. So the client's going to send some data. It's going to say, hey, here's a random number. The server is going to respond by signing the random number. It's going to sign, maybe that's just whatever time it is right now. It could be anything. They're going to do some communicating. They're going to communicate using the public key. Server is going to respond by signing some stuff. The client is going to send something to the server that's encrypted with the public key. It's some random bytes. That's going to be what they're going to use via AES to actually communicate, because now the client can encrypt stuff and send it to the server. The server can encrypt stuff and send it to the client. But because that key is encrypted with the public key, only the server can actually see the key they're using to communicate. So as long as the certificate authority is good and the server's private key hasn't been compromised, the client can connect, say, I want to use this as my password. The server just nods because of course it does, and they start communicating. TLS provides a little more privacy and security. It simplifies some of the steps down into 1 or 2 steps, and it adds some more information to the actual certificate that allows the client to trust the server with less steps. And it allows the server to trust the client better, because the client says, hey, I want to use TLS. Oh, okay, well, now we have less stuff to do to actually start communicating. I looked at a diagram earlier. It was for this particular web server. It took 300 milliseconds for SSL handshakes to be completed, and it took 200 milliseconds for TLS to be completed, which is essentially, it takes 0.3 seconds for this, it takes 0.2 seconds for this. This is better when you have to deal with hundreds of millions of maybe trillions or billions of web requests every day. So it's pretty much the same diagram. There's a lot less steps. They agree on how they're going to communicate. There's no extra, hey, I just want to make sure that you are who you say you are. That information that they needed to communicate is in the certificate, so they can just start communicating way faster. They are different. TLS is more secure. It's also just newer and keeps getting updated. SSL gets updates. Libraries that use SSL, they try to patch their vulnerabilities, but TLS is going to get all the new bells and whistles. Eventually, SSL, it just got ruled out. TLS was proposed in 1999. I have a link to a website that actually keeps track of the official documentation they proposed when they put forth the standard. If you're interested, you can read that. It actually mentions how they're going to use RSA, how they're going to use AES, or other encryption standards if you don't want to use AES. But yeah. Any questions? Anybody not get the code to work? Feel free to throw random gibberish in general. No one will be able to read it, but you can always share keys and then communicate with people in secret through general.
I did read somewhere that Google engineers did find some way to crack SSL. Forgetting exactly what they did.
SSL is pretty bad.
But they did manage to crack it, and that's how they're like, no, use TLS for everything. What else?
You said it was Google?
It was Google engineers. So Google revealed major flaw.
Google reveals major flaw in outdated but widely used SSL protocol. 2014. Very cool protocol. Very good for understanding how this works. Not very useful. But